Hello everyone. Today I'm going to talk to you about efficient constructions of pairing-based accumulators. My name is Ioanna Karantaidou, and this is joint work with my advisor Foteini Baldimtsi. So I will start with the motivation for using accumulators. This is the set membership problem. We have members of an organization, and then we have entities that want to prove their membership in that list. So if we keep that as a list of elements, we need linear storage. And depending on whether this is an ordered list or not, we would need expensive updates or expensive lookup operations for verification. And on top of that, adding privacy would also be expensive. So let's see what happens if we use an accumulator. Here we have the following entities. We have a manager that maintains an accumulator value. And we have a set of members that hold membership witnesses. And then we have a verifier that has access to the public accumulator value. If we want to add an element X, the accumulator manager would have to update the accumulator value and broadcast an update message to the rest of the previous members so they can update their witnesses. And then user X would send that witness to the verifier, and the verifier would use the witness and the accumulator value to verify membership. This way, we can have a constant accumulator value, a constant witness size, and a constant time to update the witnesses and also verify membership. Accumulators can be categorized according to whether we can add elements or delete elements. A dynamic accumulator is one where you can do both. And another distinction would be on whether you can prove membership. That would be a positive accumulator. Whether you can prove non-membership, or whether you can prove both, and that would be a universal accumulator. About security, we want, if an element X is in the accumulator, we want the verification membership to output 1, and if an element is not in the accumulator, we want the membership verification to output 0. Here we give a comparison of the most well-known instantiations. We exclude Merkle trees because we said we care about constant witness size. So we have the RSA-based accumulators that are defined over hidden order groups and accumulate prime numbers, as opposed to bilinear pairing-based accumulators that are defined on known order groups and accumulate integers. And because of this flexibility in the domain, they have been used to represent zero-knowledge sets. RSA accumulators are usually preferred because of their constant parameters, but in our case, where we have a manager for most of the operations, we can do with constant parameters as well. We have the following settings. We have the trapdoor-based setting, where the manager holds the secret that was used during the setup. This is the one I presented to you already, and some applications for that would be, for example, anonymous credentials or subscription-based services, as we discussed. Another setting is the trapdoorless setting. This is used when the entity that creates the witnesses is untrusted. An example for that would be the server in an outsourced storage environment, or the users in a decentralized blockchain environment. In this talk, we will focus on the trapdoor-based setting, and we will use bilinear pairing accumulators. Now, some problems with accumulators are unnecessary updates in the case where we only care about membership. Also expensive non-membership operations. And finally, computational overhead if we care about hiding the set. And the question would be, can we do better with a manager and by using modular constructions? We answer this question with the following three constructions. One is a positive accumulator with optimal communication cost. Then we have a universal accumulator with cheap non-membership. And then we also have a zero-knowledge accumulator with cheap non-membership and witness updates. Let's move to our first construction. This is the positive accumulator where you can prove membership. There is this result by Camacho et al. That says that the optimal communication bound for positive accumulators where we care about proving membership is linear to the number of deletions. And intuitively, this holds because imagine if I hold a membership witness and then an addition happens, my witness is still valid. So we use this result by Baldimtsi et al. That describes a modular construction for a positive accumulator by combining accumulators with different security properties. It works like this. The manager adds X, R in an adaptively sound positive additive accumulator. It means you only add elements. And then they also add the same randomness in a non-adaptively sound positive dynamic accumulator. Here you can both add and remove R. And then you get an adaptively sound positive dynamic accumulator with optimal communication cost. So there's only updates during deletions. And in our paper, we give an instantiation for accumulator 2 in the bilinear pairing setting. And for accumulator 1, you can picture any compatible signature scheme where you add elements by signing them. So as you can see, we don't need to update witnesses during additions, and we don't need to communicate updates during addition, so we get the optimal communication cost. Everything else remains constant. Moving to our second construction, this is a universal accumulator. And let me remind you here that the problem was the expensive non-membership in both instantiations. And an idea is to use two different accumulators, one for members and one for non-members. So non-membership now corresponds to membership in accumulator 2. And because we trust the manager, we don't need a disjointness proof for the two sets. This is how the construction looks like. And in our paper, we prove that because accumulator 1 and accumulator 2 are of the same type, it is secure to instantiate both of them with the same parameters. So here, any cost related to non-membership drops to constant, and all the costs are now constant, and we get both membership and non-membership. And finally, our third construction is an application of a previous universal accumulator, and it has to do with zero-knowledge accumulators. So let me define a zero-knowledge accumulator for you. We have a malicious verifier that can see the accumulator value and a couple of witnesses, let's say here for X1 and X2, and we want to prevent them from inferring anything else about the set. On top of that, if an update happens and the verifier can see the updated accumulator value, we want them to not be able to infer anything about the set, not even if X1 or X2 are still in the set. We have an instantiation in the pairing-based setting by Goss et al., but unfortunately, non-membership witness update requires a non-membership witness creation from scratch. and this one has a cost linear to the size of the set. So if we use our modular universal construction, we can replace non-membership witness update with a membership witness update and drop that cost back to constant. This was a summary of our constructions. You can find our full paper on ePrint, and thank you so much for your time.